My name is Abubakar and today I'll be presenting SHARD, a fine-grained kernel specialization in hardening framework. So, kernel code bases are gigantic and they continue to grow. As the graph shows, in the last 20 years, the Linux kernel alone has grown by a staggering 20 plus million lines of code. Unfortunately, large code size means an unnecessarily large attack surface and potentially more vulnerabilities and exploits available to an adversary. Consequently, there is a need to reduce the kernel code size for improving its security. This has been analyzed and established by multiple previous works. One way to achieve kernel code size reduction is through specialization. Notice that not all of the kernel code that we talked about earlier is going to be needed in a particular context. Applications and workloads typically require a very small subset of the kernel's code. So the kernel code size can be reduced by specializing the kernel for its intended use case, where only the code that you need in that use case is going to be available and the rest is going to be made unavailable or inaccessible. Let's see how this works in practice. Application-driven kernel specialization is a promising approach for specializing the kernel. It works as follows. Let's say I'm running NGINX and Redis on a Linux machine. Both will have their own customized kernel view. For example, Redis can only access the code that it actually needs. The rest of the code is made inaccessible to it. Same is the case with NGINX. It can access the code it needs, and the rest is unavailable. This approach provides drastic code size reductions. However, it also suffers from two key limitations. Number one, having a coarse granularity of specialization, and number two, incorrectly identifying what kernel code is actually needed. Let's talk about granularity in a bit more detail. Application specialization still exposes a large attack surface. For instance, in case of NGINX, approximately 10% of the kernel's code is exposed to the application, and this code is at the disposal of a potential adversary. As we saw earlier, kernels are gigantic, and so even having 10% of the kernel available to the adversary is a huge deficit. Now coming to the code identification problem. Existing approaches do code identification or the code that is needed by the application using two techniques. First is dynamic analysis. We run the workload offline and we record all kernel code that executes. This code is supposed to be needed by the application. Unfortunately, this approach is incomplete as it is difficult to explore all possible code paths or all possible workloads offline. Thus, dynamic analysis underestimates the kernel code needed by the application. The second approach is to use static analysis. The kernel code source code is used to construct its control flow graph. Then we identify all code paths in the kernel that are reachable from all system calls made by the application. This is the code that is then said to be required by the application. Now, kernel control flow graph generation techniques are highly imprecise, and thus the resulting specialization contains lots of false positives. To solve these two challenges, we propose SHARD, a fine-grained kernel specialization framework that provides strong security guarantees. SHARD applies specialization at the granularity of both system calls and applications to achieve drastic code size reductions. Besides, it also introduces the concept of context-aware hardening to deal with the problem of incorrect code identification. Its fine-grained specialization allows it to achieve 17 times more reduction than application-driven specialization techniques. Finally, it incurs a low to moderate overhead of 3 to 37% when deployed at runtime. To solve the problem of coarse granularity, SHARD adopts a two-dimensional specialization approach. It provides a different kernel view to each system call and in each application. For example, when NGINX makes the read system call, it is only allowed access to the code that the read system call needs when called with NGINX. Similarly, when it makes the write system call, it cannot access the code of the read system call and can only access the code needed by the write system call. Similarly, read and write system calls made by Redis can only access the code that they need respectively. Note that the code required by read in Redis and read in NGINX may be different, as we are performing specialization at both system call and application level, and applications can use system calls in very different contexts. Now coming to the problem of incorrect code identification. To deal with this problem, SHARD uses context-aware hardening. Recall that dynamic and static analysis have a huge discrepancy in the amount of reachable code that they report. For example, on NGINX, dynamic analysis reports 0.5% of the kernel code as needed per system call on average. On the other hand, static analysis reports 45.52% of the kernel code as needed per system call on average. The true value lies somewhere between these two numbers. And so we use a hybrid approach to get a more accurate value. This gives us 3 layers of code. First is the reachable code, which is the intersection of the dynamic and the static analysis, and we know that it's going to execute at runtime. Second is the potentially reachable code, which is just part of the static analysis. Finally, we have the unreachable code, which is part of neither the static nor the dynamic analysis. So what security policy should we apply for each of these layers? The choice is clear for the reachable code and the unreachable code, but what about the potentially reachable code? This code needs special treatment. If we encounter this code at runtime, it is possible that it's a genuine execution, but it's also possible that it's a malicious execution. So we allow this code to execute at runtime, but we harden its execution to prevent its malicious use. For our implementation, we use a combination of control flow integrity and shadow stack as the hardening mechanisms. Note that these techniques have a high performance overhead, which makes them impractical for the entire kernel. SHARD avoids this overhead by applying these techniques selectively to potentially reachable code only. We observe that potentially reachable code executes very infrequently at runtime, and consequently, context-aware hardening has a low performance overhead for the same hardening checks. This slide summarizes SHARD's workflow. SHARD operates in 3 steps. In the offline step, it runs dynamic analysis and static analysis to identify the reachable, potentially reachable, and unreachable kernel code for each system call. It then creates specialized copies of the kernel code for each system call. Finally, it uses these specialized copies to provide a unique kernel view to each system call that enforces both specialization and context-aware hardening at runtime. Let's talk about this last step in a bit more detail. SHARD provides specialization to guest kernels running in virtual environments. It uses Intel's extended page tables to update the kernel view on the fly. It will redirect the kernel view to one of the specialized kernel code copies that we created in the kernel instrumentation phase. For example, when the read system call is made by NGINX, SHARD will trap the execution of the system call, and it will change the kernel view to read's specialized code copy for NGINX. Similarly, when the write system call is made, the kernel view is specialized for write. By changing the translation of the guest kernel's code section, SHARD can efficiently change the guest kernel's view. Now let's move on to the evaluation of the system. SHARD's performance results are very encouraging. On SPEC CPU benchmarks, SHARD incurs a minor overhead of 0 to 2.7%. Additionally, we tested the Redis server with SHARD using the Redis benchmark test suite, which evaluates the performance of different Redis commands. SHARD incurs an overhead of 3 to 10% across the entire Redis command suite. Finally, we tested NGINX server using the Apache benchmark with 50 concurrent clients. Each of these clients requests a varying number of file size. We observed that on small file sizes, the overhead of SHARD is comparatively high. But this overhead amortizes as we go towards more realistic file sizes. SHARD gives encouraging performance results because of its efficient kernel view switching and its use of context-aware hardening instead of full kernel hardening. Now, moving on to the security evaluation. The main purpose of SHARD is to reduce the exposed code size. We only measure the reachable code as part of the exposed code, as the rest of the code is either unreachable or protected with hardening. This graph shows the percentage of kernel instructions available to different system calls of NGINX and Redis, and application specialization, as well as in case of SHARD. The graph only shows the 10 system calls with the highest instruction coverage for Redis and NGINX. Notice that application specialization will provide the same kernel view to each system call. That is why we have the straight lines for this approach. We observe that even in the worst case on the send file system call running with NGINX, SHARD provides a 1.9 times reduction as compared to application specialization. On average, across all system calls, SHARD provides a 17.6 times improvement over application-driven specialization. And with respect to the native kernel, this amounts to 181 times reduction on average across all system calls. Finally, we also evaluated SHARD's robustness against real-world control flow hijacking exploits. We tested SHARD against combinations of 10 randomly chosen vulnerabilities with 5 exploit payloads, a total of 50 attack scenarios. SHARD is able to prevent 45 out of these 50 attack scenarios, which shows SHARD's strong security robustness. In conclusion, we have seen how kernel specialization can improve a system's security. SHARD does this specialization at the granularity of both system calls and applications. It provides strong security guarantees by employing context-aware hardening. It is able to achieve a 181 times reduction in code size with respect to the native kernel and incurs a moderate overhead. Thank you everyone for listening. The source code for SHARD is available online. If you have any questions or feedback, I can be reached at bucker95@gmail.com. Finally, we would like to thank the Office of Naval Research for sponsoring this project.